If it ain't hot, it ain't happening, baby.
We're live. Is the logo set up? Here we go. How do I make a thing? My favorite thing is to make the little comment banners. Hello, everybody.
I don't think I can see those. Oh, maybe if I go.
Welcome to Antria Live with Stoycos. Scott's here.
You're really good at saying my name.
Good morning, Scott. At least Scott showed up. All right, let's get into it. Andrew Stoycos from Red Hat. Do you want to introduce yourself? Did you invite your Red Hat friends to come?
Yeah, I gave them a shout out.
Where
we'll
are
see
they?
if anything showed up. I don't know.
Okay.
They're all busy. Yeah, so I'm Andrew Stoycos. Work over at Red Hat in the office of CTO, mostly upstream Kubernetes, and more recently been exploring the wide and dangerous world of eBPF. And so here we are.
Okay, it's 23 o'clock in Israel. Oof. Where's Steve Watt? Where's your boss?
Well, doing something boss worthy.
Tell him to get out of the meetings, whatever meeting he's in. Leave. Okay, where are you? You're here, right? This is an exciting show because we haven't done a KPNG update for a couple episodes. So for folks that don't know about it, KPNG is this new backend. It was originally written by Mikhail Clouseau, and then we kind of adopted it as a sort of a community, and we've taken it all over, and we've added all these backends to it. Some of them are hacked together, like the IP tables one. We literally transmogrified the code from upstream into KPNG, and we adapted it. And
but the eBPF one is fully new, hopefully using all the powers that KPNG gives you.
Exactly. So there's two different ways to build a proxy in KPNG. One is by using this this data model where you directly respond to like services and endpoints, and then there's another one where you sort of send the entire state of the global network data model directly over gRPC down to a backend. Mm-hmm. Totally allows you to run separate backends from front ends. And so the interesting thing, as an example of what that looks like, is like the entire state space of a Kubernetes network looks something like this. Okay, so you can send this entire thing as a data structure down to a backend proxy that's running somewhere else. And Stoycos has implemented eBPF from scratch, which is real interesting, and send this whole thing down and then read each one of these one at a time and write all the endpoints and all the services out. Oh my God, what is going on? I've never seen. What? Who is spamming us?
What was that?
Okay, luckily that's not getting streamed, right?
What? I'm not seeing anything.
Okay, something. Wow. Okay, so that was weird. I have no idea what just happened. Okay, so.
I don't even see. Oh, because you
I'm
have.
glad nobody YouTube saw what I just saw. Okay, great. So something went on YouTube and some bot started spamming us.
Oh, wild.
No. Oh God. So something went on YouTube and some bot started spamming us. All right. How do we get rid of that bot? All right. Sorry, folks.
Oh no, I see it.
Something I've never.
You can block. I just blocked it. I blocked the bot.
Okay.
Yeah, great. And I'm gonna report the bot
bot
as unwanted content, commercial content, or spam and hate speech. Wait, is it hate speech? What is it?
You call it whatever you want. It's pretty bad. Okay, so I'll edit that out later, or whatever that was, if it showed up in the comments. Anyways, here we go. So Stoycos made a eBPF backend, which is, I mean, this is really exciting. Mikhail did the NFT one originally, right? So for folks that are new to the kube proxy, there's different backends that write proxying rules, and that's how the service IP addresses wind up getting forwarded to pods, right? In any Kubernetes cluster. And Stoycos, the original implementation was done by Mikhail as a PLC of how to use NF tables, which is a replacement for IP tables. But ever since then, all we were trying to do is play catch up and implement all the upstream kube proxy backends. But Stoycos has the first person in the history of the whole world to write a backend using a completely new technology with KPNG. So he wins the gold star for today.
It's just a POC. Right now it works with cluster IP and TCP and UDP protocols. So still have a long way to go, but it's a good start.
So let me fetch the latest here. And then to run KPNG, it's real easy to test it out for folks that want to try it. All you got to do is just this hack like this. You just got to run this. We'll see if it works. We did a very quick test of it earlier. It looked like it wasn't working, but we'll double check. And I think the reason was because of my system, but we can figure that out.
I need to give some kernel level requirements. I'm running on a pretty up-to-date kernel.
So all you have to do, and I'm going to put the KPNG architecture diagram, SVG, here it is.
And the interesting thing on the control plane side of things with KPNG is the NFT backend does implement this kind of full state model where anytime there's an update to services or endpoints, you get the full state of the world. So it's essentially a level-driven controller, whereas the IP tables backend, as it stands right now, implements more of a event-driven controller where you're responding to endpoint and service events. And, Kubernetes, writing Kubernetes controllers is kind of like, the suggested way is to always do it level-driven. So it's cool to see both approaches, but it would be nice if, as a community, we could converge on one way or the other, at least with KPNG.
Well, So there's two ways to build one of these. So as this comes up, we'll put this on the side over here. So this is coming up, and then so it's coming up. And so when we run test-d2e.sh, it creates a kind cluster. And inside that kind cluster, it disables the kube proxy, right? And because you can run kind with the disabled kube proxy, and then that comes up, and then it installs KPNG as an alternate kube proxy afterwards. We'll see that in a second. Dimitri, I see you here. Since this is a live stream, it's usually a cameras on live stream, so you got to hang out with us. But I'm really glad you're here because Dimitri is writing the kube proxy updates for the Windows kernel space, right? So we have this one here. Maybe he's even got an update for us. So we have this other one, which is the Windows kernel space. So I made this MR originally. And now Dimitri's kind of taking it over. And this one, I'll show you all what Stoycos is talking about in here. So this is the Windows implementation. And so we could see here set service, right? We can see here the set service, delete service. Like this is why Stoycos is saying this isn't like an event-driven implementation where every time a service is created, we update the Windows proxy rules. Every time an endpoint is created, we update the Windows proxy rules. This is kind of how Kubernetes currently works, right?
But they don't suggest that, right? The official how to write a Kubernetes controller leans heavy towards writing a level-driven controller rather than event-driven. So.
It's like we actually really we actually have documentation about that upstream. I didn't know we had that. Okay.
Yeah, let me find it. There's a reference upstream controller.
Right. Anyways, the point is that wrong or right, this is the way the IP tables proxy works in the current Kubernetes and also how it works in KPNG because we basically ripped all that code out and got it working in Kubernetes. But that's not how KPNG was really designed to be run. The way it was really designed to be run is that you take the entire state space, and then this is what you're calling a level-driven controller. Is that?
Yeah.
Okay.
I can show what I'm talking about if you want.
Just give me the link, and then I think you're going to take over in a minute anyways.
Yeah, let me get the link.
Once this thing blows up and you tell us why. Do whatever you want. It's your show.
We need more folks to start breaking everything I've written. That's for sure. That's the fun part.
Yeah.
So let me show you what I'm talking about. You can bring it up. Ebpf.
Okay, where is the current show, by the way? I'm trying to find where we... trying to make sure this is...
Here, you can pull that up on your screen if you want. I put it in the private chat and in the YouTube comments.
Where is... Okay, I want to get to the YouTube link.
Oh, I got it right here. I have it up on the page.
Do you have it? Can you paste that to me really quick somehow?
Yeah, I put it in the private chat.
Okay, private chat. All right, here we go. Because I want to update that with to be in the playlist just in case folks don't see. Where is it? Add to. How do I add to play? Yeah, save. Here we go. Control live. There we go. Okay, cool. So now this is in the playlist. Got it. All right. So where was the
what are you looking for?
You have where's the link? You put sample controller. Is that it?
That's the actual Kubernetes reference. Go to the one.
Okay, well, so they define this. Where do they say level controller?
I don't know if they do here, but if you actually look through it, I'm pretty sure it's a level-driven controller. And on Kubernetes main documentation page, they reference that.
Why is this taking so long?
It's done. It's already failed. Go look at it.
Okay, let's see. It failed. All right, cool. All right, so we can see here, we created this new cluster, and then deleted the existing kube proxy, and then we loaded the compiled images that have this from stoycos' fork in it, and then this sort of came up, but let's see, kubectl get pods -a. Okay, so we can see here.
Broke it.
We see, yeah, we can see that these are all in crash back off. So let's look at the KPNG. So a regular kube proxy, right, has these running on every node, right? So kubectl get nodes. We can see here that there's 3 nodes here. And
it's a daemon set. Yep.
Exactly. This is a daemon set. This is running on all 3 nodes, and it's not coming up. So we just never know who's watching stoycos. I know that you know that. I know that you know what a daemon set is.
Someone could not. Fair enough.
Someone might not know how this. Okay, so
when we spin up the Bpf backend, I also pulled in an extra container to help us diagnose things. I am using Cilium's Bpf Tool container so that we can get the Bpf Tool binary and kind of analyze our program. But it's not doing anything functionality-wise. All of the actual stuff is running in the KPNG-eBpf.
Okay. So we have, if I look at the pod, broken. Okay, so if I go in here and I look at this pod, let's see what's in here, and we'll see why this isn't working. Okay, so where is it? Image. Here we go. Okay, so I've got a Cilium Bpf tool. So you've got that in here for debugging.
Yeah.
And then we've got KPNG
test for both of the other 2 containers.
Yeah, for the other 2 containers. Yeah, that's
one
the
is
KPNG. Yeah.
Right. One is running the KPNG server, which is essentially watching the API. Yep. And then the other is running the KPNG client and the eBpf backend.
Yeah. So exactly. So we should see when we did the describe on the pod, right? We saw.
Yeah, you need to do the logs. Check out the logs in that pod that's crashing.
Yeah.
Or in the container that's crashing in the pod. Yeah. It's the KPNG-eBpf container.
Okay, here we go. Logs. Okay, there we go. Come on. Okay. -c KP. Okay. So, all right, one at a time. So we've got 3 containers in this pod. So there's nothing in here. Right?
Nothing there. There's going to be.
And this should be fine because this is all this thing is doing is watching.
Yeah.
So this container, for folks that are new to KPNG, this container, as Andrew said, I'll say it again, this thing is just watching the API server. So this is this part over here, right? It's watching the API server, and it's just saying, hey, what services and what endpoints are there, because I'll write those networking rules for you. That's what that's half of what the kube proxy does. The other half is it goes and it writes IP tables rules on your node, right? So now we look at the other container, and we'll see where that's failing. So the container that is failing is the one that's trying to write eBPF rules. So let's see why it's failing. Okay, so explain this to us.
So essentially, BTF is a part of Bpf that essentially encodes debugging information into the compiled Bpf programs. And my guess is that your kernel is pretty old. So what does uname-r show on your machine?
Okay, let's see, uname-r. Okay. How's this? Is that too old for you?
Too old. So
am I too old for you? Is this like an episode where you just make fun of us for being old?
Yeah. So my initial assumption is that you're seeing this issue because this kernel is just really old, and a lot of new BTF and Bpf support in general is a lot newer. So I'm actually running on a 5.18 kernel, and you're on 4.15. Okay. That's old.
Yeah.
So
okay.
That makes sense.
Okay,
and
cool.
What I will do a follow up to this episode is kind of define what works and what doesn't for various kernel versions. But you definitely need some newer kernels.
I want to say hi to Parrot and Junjin who just showed up.
Hello.
Where's Amin? How come Amin didn't come? I'm gonna yell at him.
Call him out. Call him out.
Come on, Amin. Okay, you ready to take over?
Yeah. Give it to me. Let's see.
All right, let's see here. All right, how do I give it to you? Okay, so Stoycos has a computer that was made in this century, and he's gonna, go ahead and turn your screen share on.
Okay.
Kernels won't work.
I just turned it on. Can we see my screen?
Yeah.
Cool.
Okay, the show. Little
awesome.
Okay, here we go. Now I see your screen. Awesome. Okay.
So let's check out what kernel my machine's running on. Running with. As I said before, I'm on 5.18.6.
Okay.
Coming from Jay's 4.15. So pretty old. There's probably a lot of dependencies missing on that old of a kernel. So, and remember, this is kind of a funny deployment scenario for eBPF programs. So if you don't know what eBPF programs are, there's a bunch of great resources online. I'm happy to point them out to you. But essentially, when you run eBPF programs like on Docker containers or within Docker containers, really at the end of the day, all that matters is the kernel version on your underlying system. So that's why this is really important. So it failed to spin up on Jay's cluster, but let's check out if things are working over here. Oh, I'm in the wrong thing. Sorry. I'm in a container. Awesome. In this case, everything is up and running. A little bit old. I actually haven't had to tear this down in a while, which is nice. But we have our KPNG pods with all three containers as we were seeing before.
Okay. So now we're trying to do this again. We're doing it in okay. So you've already got this all. He's already run the steps that I just ran, except he's running it on a
much more modern server.
But I don't get. Hold on. Are you SSH into a Linux box somewhere?
Yep. So look, cool. Can you see down here? I'm on.
It's just so confusing because you're in VS Code, and I'm like, okay. See, I shamed a meme into coming.
Ah, he's here. So in the deployment, you can see we have three containers as we talked about before. Ebpf tools, which I've just started to essentially allow us to debug. And it also mounts the Bpf file system, which is kind of an important step. The KPNG container, which is running the service API.
Is my microphone still working? Because I was using the wrong mic. It sounds a lot better now, doesn't it?
It sounds kind of the same.
Jesus.
I think.
Okay. Let me reload. Hold on. I'm going to reload.
Okay. And then the last container is the KPNG eBPF container, which is actually running all of the business logic, i.e. loading the Bpf bytecode into the kernel. Okay. So can you see now, Jay? Are you back?
Do I sound the same?
Yeah, you sound fine though. You don't sound bad.
Fine, whatever.
Fine.
You might just not have any taste.
I probably don't.
You might have like,
That's what it is.
yeah,
Audio taste.
yeah.
So why don't
You don't
we
care how shit sounds. You might just okay. Anyways, go on.
check out these backends we've been talking about for a while? Obviously, here we have IP tables, IPVS, NFT, user space, LIN, blah, blah, blah. Jay showed earlier in this program how IP tables, for example, implements sort of a, let's see, where is it in here? I can't even remember. Sort of a, yeah, right here, set service, delete service. It's essentially event-driven. Bpf does things a little differently because KPNG was designed such that we get the full state of the world in terms of services and endpoints anytime an event happens. So you can see that here. Whenever the KPNG client sees a change, this callback is essentially called.
So $40 microphone. I just want people to know.
That one sounds better.
Oh, now it sounds better.
Yeah.
So I was too far away.
Yeah, you were too far away.
Is this better, Scott? Jesus. Okay, go on. Sorry.
No, you're good. Just a little bit of distraction.
I feel like Axl Rose right now.
I don't even know who that is. But anyway, I was talking about kind of this callback function, which is how we respond to events in the eBPF backend. And you can see every
That's the
time
thing that sends the entire state space,
right,
that callback. So that client service endpoints, that's a big, huge YAML file of every Kubernetes service and every Kubernetes endpoint after it, right? And so he's showing us that channel that flows all those in. And then you just for loop through that shit.
Yep, essentially. Okay. It isn't the smartest, but it's a true level-driven controller. And thankfully, KPNG has also given us some libraries to help out with, figuring out what we need to do on each reconciliation cycle. One of these libraries is this light diff store library, which essentially just allows you to figure out if something has changed in a service, a given service or a given endpoint on every reconciliation cycle. So that's really nice. Makes things pretty easily.
And we're calling this this is a new thing, this light diff store. I don't remember it, neither does a meme. And so what can you walk us through that code really quickly before you run stuff? Okay.
The easiest way to understand that, I think, is actually to look at the tests for it.
Okay.
Boom. So diff store is kind of the core one. I think Mikhail was using that to prototype a bunch of different things with different data structures. And then light diff store is actually what he intended to be used by us. So let's check out this test and see what it does. Basically, we create a new light diff store. And the first thing we do is we store two entries. It's basically a map. So key A, value Alice, key B, value Bob. And what light diff store, the power it gives you is you can, after setting things or altering the map, you can call these updated and deleted functions. And it'll basically tell you what's happened since the last time you reset the diff store. So I wonder if I can actually run this with logs.
Yeah, so exactly. So this is a way of, for some history here, the way the kernel space kube proxy works is it basically in memory calculates the difference every single time a change happens and says, has the network state space changed or not? And if so, it has a little data model in memory that it modifies and it sets a changed bit. And then every I don't know, I think it's like every second or something, the existing kernel space kube proxy goes and it looks at that state space and it rewrites networking rules. So what the way KPNG handles this sort of similar problem of calculating the differences, when you're using this proxy type, there's two types of proxies as in KPNG, as we've shown. And that when you're doing the type that actually reads the entire networking state space every time, you have this problem, which is that you're reading in the entire state space. So you need to calculate a diff somehow because you have the entire state space a minute ago and now. So this is the tool that Mikhail put into the project to allow us to calculate this diff. So you write, you hit a reset, and then you write. And now you can see the difference between the first batch of writes and the second batch of writes.
Yeah, and I actually was poking around at the test earlier and broke it so that we could see what's going on here, basically.
Why is it called light diff store?
Because diff store was essentially, when I asked Mikhail about this, and he said diff store was like his attempt to just prototype things. And, you know, here he used a couple different data structures. And in light diff store, it's literally just using a B tree at its core, I believe. So if we go in
it's
here,
always been a B tree though.
Right here. Yeah, but I think in diff store, no, see in diff store, he was trying to use a buffer. Like he was just experimenting with different things. So
wait, what do you think about this? Andrew just shows up and then he starts telling us how everything works.
Well, I had to figure out how to use a light diff store in the eBpf backend. So that's where we're at. But this is kind of cool. So I can see what this test is failing because I forced it to fail, but you can essentially see we add 2 new entries, one for A corresponding to a value of Alice, one for B corresponding to a value of Bob. And then when we print map.updated, we can see that those 2 entries were added. So put this in the context of services. If we created 2 new services, when you dumped s.updated, you would see, oh, okay, here's 2 new services we need to add into our data plane. So that's why it's so nice.
Yeah.
So taking it back.
Yeah,
so
let's go back. Okay, sorry about that. I just wanted to.
No, it's good.
So now this is the meat of it. This is the part that's really doing all the rules. So let's show us how this new,
So there's a lot going on here. Basically, I started by looking at what Cilium has kind of done and seeing like what we had to do to remove it from their control plane. So that's what we've done here. Right now, what I'm showing you is still in the control plane side of things. We're not in the data plane yet. So in the control plane, we essentially are looping through all of our known services and endpoints. And then we are boiling all this information down into the exact information we need for the data plane, which is eBpf. Yeah. Okay. So all this is kind of pedantics. At the end of the day, we're storing the information we need into a light diff store, which is it's called here EBC service map. And after that, we say, okay, if anything's changed, i.e. if the diff store updated has any entries or diff store deleted has any entries.
The EBC is the new data structure that you're implementing the light diff store interface with?
Yeah, it's essentially just what I've used to reference like an eBpf controller, right? So it holds some things like references to our Bpf programs, IP family, and then the most important thing is it holds basically an in-memory cache of what's going on in our services and endpoints world, right?
Yeah. Okay. So you're okay. All right. I'm sorry. It's not an interface though. It's an actual struct. So
it's an actual struct. Yeah.
The diff store is a struct, and it's a generic struct, and it takes in the generics, and you've programmed it for what are the generic types in there?
The generic types in this one are actually a service endpoint mapping. So a service map stores a key.
Oh, so you didn't have to put anything special in there.
No, it's super simple. That's why I tried to boil it all down into like super simple control plane. Okay. And so all we're doing is we make a key that's made out of the namespace name for a service. Namespace name is literally just the name of the service and the namespace it's in. So it's unique. The specific port for that service. So a single service could have multiple entries and multiple ports. And then the protocol for that service, right? For that service endpoint mapping. So that's what I'm doing in the control plane, keeping track of that. And then upon a sync event, so if we want to sync, if the state has changed, this is how we tell if state has changed by checking if there were any updated or any deleted. Then we go down here and sync. This is where things get a little more fun, I think.
So now you're starting to do logic that's specific to eBpf. almost.
Not even.
Not yet, huh? Make Ebpf Maps. It's 159.
Right. This is total. Everything I'm showing you right now is in Go. So everything in Go defines my control plane. All of the data plane components are actually written in C. So I'll go look at that. Yeah, we'll go look at that a little bit later. But the way that my Go program confers with my C program is with this concept of Ebpf Maps. Okay. So basically what I do in sync is I load those Ebpf maps with the data that represents my current services and endpoints. So this is for deleting, but if we look at all of the entities that were updated since the last iteration, we are then going to add corresponding entries for a given service.
What do you mean period syncs? I mean, what are you talking about? Periodic syncs? Period.
I can't see his. I can't see.
He said, "How are you handling period syncs?"
Periodic syncs. We're not doing any periodic syncs. I don't think, unless
he's doing this full state. I mean,
yeah, this is totally full state. So the only time you're triggering a sync is essentially whenever an event happens on the API side of things. Like if an endpoint goes away, then we'll get a whole new full state.
Yeah, so that's only for legacy proxies. You know how hard Ebpf has been working since he's asking these questions. That's how you know he's been dealing with customer issues for the past month and a half, because he forgot how how KPNG works. So you know he wrote the entire user space Windows proxy here.
Yeah, I know.
Yeah. So Ebpf, this is a full state. Yeah, this is full state. So there's no periodic anything. In the I'll say it again because there's a lot of new people here, I'm sure, that are going to watch this. In the existing kernel space kube proxy and in the KPNG IP tables implementation, we do periodic syncs. In other words, there's a data structure that's sitting there and that's figuring out what the differences are in memory, and then every like 1 second, if there is a difference in the way in the pods or the services in all of Kubernetes, that needs to be written out so that you can write new IP tables rules, like a pod got deleted and a new pod came up, or a service got created or whatever. Those new IP tables rules are written, and there's a thing that's periodically running that. So there's
that's seen right here. Yeah, I'm in user space LIN now. You see, like literally we're calling on any of those events, we're calling set service, delete service, blah, blah, blah. Exactly. It was a shim to make it easier to interact with the existing
for dumb people like me, so idiots like me could copy paste.
No, it made sense. It made sense then, but it has made it a bit confusing for people who are new coming in to write a new backend. Like I want to standardize this. Like I want to do it either with a set service or with a generic callback full state every time sort of thing. Right.
Okay. That's fair. Okay. Keep going. Where were we? So we were just about to load those Ebpf maps. So you calculated the diff. You got the light diff store. Now you know what rules you need to write to update your
Bpf maps,
your cluster, so that the new hypothetical scenario, a new cluster IP service was created, and it's supposed to forward traffic to these 5 different pods, and maybe 3 out of those 5 pods are up. So let's say, okay, what happens now?
So now we write the relevant information into an Ebpf map. So the Ebpf map, right, is a really important concept. It's how you get data from your control plane program, in this case, written in Go, to your data plane program, in this case, running in the kernel with a Bpf program.
Okay. Now, can you tell us, because it was in the show title, how is this different than what we do when we do IP tables proxying?
So IP tables is basically like a rule-based proxyer. As you write more rules, like for every packet, you essentially have to loop through all the rules and make a match or not. And you interact with it in user space, right, with just a simple IP tables command. And it's handling natting, interacting with contract. It's handling a lot of things. The way this C program works is very, very different. And I'll talk through that when we go into the actual C program. How about that? Because it would be kind of confusing to bring up yet. Sound good?
Are Ebpf programs Turing complete?
Say again?
Are eBPF programs, are they like Turing complete? Like, can you put anything? Can you put for loops in there? Can you put while loops in there? Can you do anything you want?
No, you're very limited. You cannot. Basically, there's a verifier that is called whenever you're trying to load a program. And if you are going to do something that's totally breaking your kernel, like an infinite loop, you can't do it. You're not allowed to. You're put in a safe box.
But they do have all the basic constructs of a programming language.
Most of them, yeah. And we'll go look at you can't, there's some constraints, and I'm not going to list them all out right now, but they're pretty easy to find. But we'll show the C program that's actually running here. But
there's a big Reddit thread about whether eBPF is Turing complete or not. This is a big fight on the internet.
Oh, really? I didn't know that.
People are fighting about it.
That's funny.
Yeah. Evidently, it is Turing complete. Okay, I don't know, but some people say it's not. I don't know. Just keep going. Sorry. Okay.
No, you're good. So what we're gonna do now is we got to the point in our control plane code where we were writing to Bpf maps. So let's go actually check out these Bpf maps that are running on the system right now. So this is why this tools container I've added to the daemon set's really, really helpful, because we have access to Bpf Tool, which is a great program to help, analyze and debug running Bpf programs.
Okay, so Bpf Tool is a thing maintained by our friends at Cilium.
No, Bpf Tool is actually, I believe, part of LLVM. It's basically just a binary I'm using one of Cilium's pre-built images that has this tool.
Oh, okay. So Cilium makes these Docker images, and those Docker images have Bpf Tool embedded inside of them.
Because it's not super trivial to build it into Alpine at the moment, but it will be soon. And we're using Alpine for our kind setup.
Why is either one of us? You work at Red Hat and I work at VMware.
I have no idea.
Neither one of us is allowed to ship anything with Alpine. So why are you demoing this?
This was how it was. I came in a couple of weeks ago and we're here. But anyway,
we need to fix that.
Now we're in a tools container, and we can use Bpf Tool to see what's going on our system. So if we write Bpf Tool map, we can see we have 3 different copies of both a service map and backend map. And this is how we share information between our kernel and our user space program. And you can also do really interesting things like dumping what's in those maps. Let's check it out. Boom. You can actually see what's going on in those maps. And this is all added by my program.
Okay, cool.
But it's pretty confusing. It is in network endian, and you're seeing it all in.
So go to the top of it. Is there like because that just looks like a big JSON thing.
Basically, this is just how Bpf Tool dumps it.
So when you run Bpf Tool, map dump ID 133. So what is 133? That's the
133 is what I got. It's the ID of the map. So here, each container is maintaining 2 maps, a service map and a backend map. The reason we see all 3 of those in kind is because at the end of the day, all these Bpf programs are running on a single node. So there is no concept of namespaces for Bpf programs yet. So therefore we see everything. It's just an unfortunate fact of running this in kind. At least I haven't found a solution yet around it. Does that make sense, Jay? See how we literally have 3 different copies of v4 service map, v4 backend map, all with different IDs.
Oh, I get it. Okay. So that's why you've got 6 of those.
Yeah, but
so you've got 2 per node. So can you just highlight so we give people a visual of? Can you highlight 124 and 125?
Yeah,
or one of them, like a set, like one of the set. Yeah, those 2. Okay, so that's running on node 3. So I have 3 nodes in my cluster, and I've got inside of the 3rd node in my cluster, I have 2 eBPF maps that have been written for me by stoycos' backend. One of them is called the service map. The other is a backend map. And each one of those maps has a bunch of bindings with a bunch of networking rules in it. Now you're going to show us all the networking rules. So which one are we going to do first? 133 again?
Yeah, why don't we do 133 and this time I'll print it out with the pretty flag, which should actually show me hex, and that's kind of nice. Cool. So now we have, this is dumping my service map. So I'll talk more about the service and endpoint map abstraction when we look at the C code.
For folks watching, you would not see this in a regular cluster because you'd be in the node and you'd be looking at one node and you'd only see two maps.
Right.
This is just a kind thing, the fact that we see everything all dumped all over the place.
Yeah. Okay, and we can even try to, well, we don't know.
No, it's fine. No, yeah, just keep going.
Cool. So that's how we see our maps. Let's now go talk about the actual Bpf program that's doing all the fun data plane bits. So that's down in the Bpf directory, and it's titled cgroup connect4.c. This is where all the magic's happening. And remember those maps we were just talking about? Well, here's where they're defined. We have our v4 service map and v4 backend maps. The v4 service map is essentially keeping track of all of our VIPs, and the v4 backend map is essentially keeping track of all of the backends or the endpoints.
So you wrote a Go program that generates C?
No, I will talk about how
a library that does this. Okay.
Yes, I'm going to talk about how these programs kind of interact after I describe what's going on in this C group.
Okay. All right, so there's a bunch of code in your KPNG backend that's generating this code, but this is the actual code that you generate that writes these rules. And this is dynamic code that you inject into the kernel in real time every time a thing changes. You regenerate this whole C program.
No, it's sitting in the kernel running and reconciling based off these maps.
Okay, so you load, it's a one-time load?
Let me say that, sorry. It's a one-time load. But this program is called whenever a connect4 syscall is made by any process. That's how Bpf works. So Bpf essentially are programs that are invocated on certain system calls. So you as a user can say whenever a user space
program. How do you give this the new, hold on, how do you give this the new data?
All via Bpf Maps.
Okay, so when you write those maps, those automatically get targeted to this
program.
How does the kernel know where to send your map to?
It's all built into the bytecode, and the bytecode is actually seen here with .o files. You can go pretty in depth. Basically, whenever I compile the C program, we maintain a reference to the maps, right? And then we also are doing that in the user space in our Go program. We're doing it on both sides.
How do you prevent another program from writing to your map?
You can't.
You can't
right now.
Okay.
Yeah.
All right. How many? Okay. So hold on. In KPNG writes these rules.
Yes.
Is there
into our two maps?
There's got to be some primary foreign key thing. There's got to be something you're putting in your KPNG code that says I want to write to this map, right?
Yes, and that's all auto-generated, and I'll talk about that a little bit.
Okay, sorry. Okay, keep going. Whatever.
So I'm not going to go super in depth into this C code because it's not extremely exciting. It's pretty easy, but I want to talk about the concept behind it. So whenever a client on a node, or in this case, something in a container on a node, whether that's curl, a Go client, a C client, we don't care. Whenever a client tries to reach out to an IP, one of the syscalls that happens is a connect4 syscall. And let me show you how kind of proof of that. I think I made note of it here. Maybe I didn't, but I did in here. Maybe I didn't actually. I have it somewhere. I know where it is.
See, maybe you need to get a mic like this. See, do you hear how good my voice sounds right now?
Oh, maybe I don't have it. But anyway, let me go back. Sorry. So as I was saying before, whenever a client...
Windows machine or a Chromebook? What is this? What do you do?
I'm on Fedora, baby.
On Fedora?
Heck yeah.
Okay, Red Hat.
Okay, so whenever a client on a Linux machine kind of reaches out to a server, a connect for syscall is made. And whenever that connect for syscall is made, this BPF program is called. Okay, does that make sense? So here's where that actually happens. Whenever a client tries to reach out to something, whether that's with curl or any other client, this connect for syscall is hit. And we call our function sock4 connect, which I've defined here, which then just calls sock4 forward. It's kind of a wrapper function. Now this function sock4 forward at a high level grabs the traffic and says, looks at the destination IP and the port and the protocol and says, do we care about this traffic? So 90% of the time we don't care, right? All we care about for a service proxy is if the traffic is destined for a VIP and a given port, right? Does that make sense?
Yeah.
So what this does is catches the first packet of a traffic destined for a VIP and a port and rewrites it before it even enters the network.
So you're loading these programs for a specific IP and port?
You're loading, loading, these programs are loaded in the kernel, just sitting there ready to go.
Yeah.
They're invocated whenever a connect for syscall is made. And then once they're invocated, they look at the values in our Ebpf map, which are basically a list of VIPs, and they look at the actual destination IP of the packet. And they say, is the destination IP of the packet one of these VIPs I know about? Does that make sense?
Okay, so so it's a generic API call to the kernel.
Yep.
You just make a generic call to the kernel, and you're saying that here's a map of VIPs, and then that data is sent to the kernel. And because eBPF was written to deal with networking, it knows how to see eBPF was written to read these IP address rules.
Well, yeah, let's check this out. So as I was saying before, whenever a connect for syscall is made, this sock4 connect program is called, and then this sock4 forward program is called. So let's look at the sock4 forward program. What's passed to the user here is a BPF sock address. And the BPF sock address is, whoa, look, it's a bunch of information about our packet. So family, IP address, destination IP address, et cetera, right? So now in our BPF program, we make a key, and the key literally looks at the user, the destination IP address of the packet, the destination port, and a backend slot, which isn't super important. It's kind of an internal subtlety. And we do a lookup to our Bpf maps, which is done here. And if we care about that IP and port, then we go do other things. Does that make sense?
It kind of does. Just keep going.
Cool. So if we catch a packet, and if the packet is destined for a service VIP, i.e. a cluster IP, sorry, I keep saying VIP, virtual IP, cluster IP, I'm using them synonymously. If we catch a packet we care about, first thing we do, because this is kind of a fun POC, is we debug. We give out a debug log, and those logs can also be accessed in that tools container. The next thing we do is we look up a backend. So we know we have a service we care about, but we need to figure out which endpoint we want to direct this connection to. And so the first lookup we did was to look up and see if we had a VIP we cared about, i.e. a service. The next lookup we do is to find a backend for that VIP. Okay?
Okay.
So once we have a backend for that VIP, then we have the information we need to rewrite this packet. We have that backend's IP, and we have the target port on the backend. So you can correlate that to an endpoint IP and an endpoint port.
And I just want to 100% confirm, this is loaded on a init of the eBPF backend.
Say that again?
This is loaded one time on the initialization of the KPNG eBPF backend.
Correct. Yes.
Okay.
The bytecode does not change. It's static.
One time load. So there's like a func init somewhere in your code here that does this.
Yep.
Yeah. Okay.
And then the last thing we do is literally rewrite the destination IP and port of the packet. And remember, this is the first packet in a connection, and this is happening before the packet has even been directed to the Linux networking stack. So we're kind of cheating. Like, we're tricking the Linux networking stack into thinking that a client is just talking to a pod. So really, we're tricking the Linux networking stack into saying that a client contacting a VIP is really just a client, is just a pod-to-pod connection. So we could actually look at that. It's kind of cool.
Why do you say tricking, though?
Because let me show you.
Everybody have this smile on their face whenever they talk about eBPF, like they're doing something wrong. Like, what?
It's not always trickery, but in this case, it's kind of cool. And it's what Cilium does. It makes a lot of sense. So right now I have a single node port. Sorry, I actually have a node port service, and I should not, because we don't support node port. Let me delete this service and bring it back up. And then what's the command?
I guess I get what you mean, because you're inside the cluster network.
It'll make a lot more sense.
And that you're inside the cluster network, and you're not writing any kind of a forwarding rule or anything. You're rewriting the packet, but you're rewriting it at a point where the packet has no problem being routed to that new place because it knows where it is.
Right.
Yeah.
So this will make it a lot more clear. We have I
think what I said makes it a lot more clear.
Well, this will make it even more clear.
Why can't you give me some credit here, man?
You get a ton of credit. You're bearing with me. It's pretty complex stuff. It's a lot to explain. And there's even more that we could do 2 whole episodes.
We've still got 7 people watching, and we're 50 minutes in. Usually people leave by now.
Well, this is exciting. So let's check this out. Here's a VIP. I just made a service. I have a really basic Nginx deployment. So 2 Nginx pods backing this service with a cluster IP of 10.96.131.115. We can go over into my temp shell. It's just a temporary client pod. We can verify that this works, right? So I'm going to curl the VIP. Ta-da! Things work.
Oh, that shit works.
But let's go check out what's actually going on. Like, what does the node see? That's what I want to see. So what node is my client on?
I just want people to realize the gravity of this. James Stewart, this is like a personal, like a self-affirmation. Okay, so James, it's good to see you, man. So I just want folks to realize the gravity of what stoycos just showed us. This is a Kubernetes-SIGs/KPNG project. This is very soon going to be eBPF supported as a proxying option in a project that is maintained by the Kubernetes community in the upstream. And
fully upstream.
If you all vote for it and tell Tim Hawken to merge it, it'll be a KEP that will eventually be the actual kube proxy. And we're very close to that.
Yeah, exactly.
We'll give that KEP a thumbs up.
So let's see what's actually happening under the covers a little bit. So I'm running TCP dump on the node where this pod is. I do my curl, and obviously we get a bunch of stuff. But let's look at the first packet of this connection. This is like the coolest thing ever, right? The first packet of connection. Mm-hmm. Let's look again. What IP did I just curl? 10.96.131.115, right? Look what the Linux networking stack sees, right? It does not see that IP anywhere. All we see is 10.244.2.3 going to 10.244.2.2. It's literally seeing pod to pod. That's it. Mm-hmm. That's the exciting part. Does that make sense? Like, we are rewriting that packet, before the first packet in the connection, before it even gets to the Linux networking stack. So it's like, we don't even have to keep state of that. We don't have to do any contracting. It just works in this case.
No contract.
No contract for this case for cluster IP services. Cool. So you can also.
You're such a big nerd. I can see how happy you are right
I'm
now.
a huge nerd. I actually found a kernel bug in this, and I'm gonna be posting a kernel patch. Try to. So I implemented some logging, so we can see whenever our Bpf program catches a packet, we can kind of see what was the backend address. Note this is in hex and it's in network.
So TCP, so that's why you say you feel like you're tricking it, because TCP dump doesn't have any idea what the hell's going on. It just, for it, it's like 2 local IP addresses that it knows how to route.
Yeah, exactly.
So now this is just a CNI problem at this point.
Yes. Now it's all going over the CNI.
This is all going, this isn't it. Yeah. This is now gone from a kube proxy routing rule IP tables problem to now it's all Andrea's problem or Calico or whatever your CNI is.
Yeah, and that's the cool part. And Cilium has been doing this forever, but Cilium really, all their code is really tightly tied to their control plane, right? And what we've done here is pull it out, that design, and apply it to the KPNG control plane. So now everyone can use it pretty easily, right? Really easily. So yeah, one last thing I'd like to talk about is we looked at our C program, we looked at our control plane Go program, but a really interesting thing that I do here is using Cilium's Ebpf library, which is their public Go Ebpf bindings, basically, which for note, they don't even use in their production code. It's kind of interesting. I can manage the compiling and loading of my Bpf programs and maps in Go. That's a pretty powerful thing too.
Okay. And that's how you're doing all this. So you're using the Golang SDK to load all the code. So it compiled, the Go SDK compiles the C code and loads it into the kernel and does all that for you.
Well, before you run your main Go program, you have to run Go generate, and it actually compiles and generates all your bytecode. So -o files are Bpf bytecode, and we can
so
actually.
Are you committing a -o file to in your PR? I didn't really look through it.
Yeah, I am.
Are we allowed to do that?
Yeah, I mean, we could do it dynamically, but
why wouldn't we? Okay, I mean, I'm not trying to nit this, but I'm just saying, like,
because you essentially
you can't version control a .o file, can you? It's just a C binary.
Actually, you're right. We probably should be building it on the fly.
Yeah, we should build it on the fly. I think on startup.
Yeah, I think we have to actually. That's probably another reason it was failing on your machine. But if we use LLVM object dump on these ELF files, you can get more information about them. So remember our Bpf program? Here it is, C group connect 4, right? That's a cool little tidbit. I use that sometimes.
So that means we have to put the Go. Hold on. So does that mean we have to put the Go binary into the eBPF KPNG backend so that when the eBPF KPNG backend starts up, it can go generate the C code that needs to be loaded into them?
Yeah, I mean, that's not a hard thing. We could essentially.
Is that how these things always work? There must be a more streamlined way of doing it.
Well,
there must be some kind of container base image that people normally use or something. If you're some fancy.
Cilium has some stuff, but a lot of it, they have like scripts that build their bytecode on the fly, right? So they don't have a Go generate, which, for everyone's info, is just wrapping Clang. They literally have a script that runs Clang and compiles their Bpf C code into bytecode.
So at the minimum, if you're running eBPF, if you were a person who was writing a container and the container's job was to load Bpf programs, you would need a C compiler in your container. Why don't they just put a thing in the kernel that can read C code?
Well, no, because bytecode is portable, and it's gotten more portable, especially with BTF. the goal for Bpf is to have compile once, run anywhere bytecode. Like, and we're getting closer to that. So that's kind of why I included just pre-compiled bytecode in here. But in reality, you know, probably for the current state of the kernel and the current state of folks not being on the bleeding edge of the kernel, it makes more sense to build on the fly. Does that make sense?
I got it. Okay.
But the end goal is to be able to compile once, run anywhere.
You know, like a middle of the road solution is you could put this .o file on like an S3 bucket, and then you could have a configuration thing in the deal that said where to pull the .o file from, or you could have some kind of a thing that mounted. You know, you could use go bin data. My favorite.
No,
right?
This could literally just
could
be a step in your building of the KPNG image.
I think you could go bin data it. I think if you go bin data it, then Go could just write this program out on the fly, and all the code would be in Go. That would be a good.
Yeah, I definitely am going to go back and think about how I do that. But anyway, so this library is nice though because it allows us in Go in our control plane world to maintain a reference to our v4 service map, our v4 backend map, the two Bpf maps we were looking at, and it also allows us to maintain a reference to our program, right? Mm-hmm. So it generates these Go bindings that give us Go representations of our program and maps. So those are right here, right? Our SOC4 Connect program and our two Bpf maps. That's how we write to those maps from user space. And how we also can, you know, once our KPNG container dies and crash loops, this is how we ensure we remove that Bpf program.
This is cool, man. Okay.
There's a lot going on.
I think we're way past, we're 2 minutes past. So, and I think this is a great stopping point, and I want to leave people wanting more. Normally everybody leaves and I'm just sitting here talking to myself. I just love dropping it. Look, somebody just joined super late. I don't know who you are, but you missed the show. I'm sorry. So, okay, let's wrap up here. So, in summary, let's go back to your stuff. So, here's the wait, I'm sharing the wrong screen, even though I kind of wanted to share that one too, but this is the one I really wanted to show. The original, here's your code. So wrapping up, here's the KPNG architecture. We saw stoycos went and he implemented a full state backend, which takes the entire Kubernetes networking space, which is
defined by the KPNG API.
Yeah, exactly. So that's here. Let me just put it up split screen so folks can see it. So doc and whoops, examples. And where is it? Here we go. Yeah. So if I go to examples and then I go to, wait, where do we put it? Doc?
Which one?
My YAML file that I always show people. I lost it.
It's wasn't it on the main directory?
Oh, it's at the bottom, right? Yeah, global state. So he's got this, right? So he's got the whole state space flowing into here, right? So he's got that whole thing, and he is sending that in to the backend, his eBPF backend, which he has just written in this beautiful PR here, right?
Yeah, it's pretty.
And so, and then what this thing is doing, okay, is this thing is going off. And why did you update all my Go mods for all the other things?
I only updated two little things, but so remember Mikhail switched to using Go workspaces. So now when like you update the API machinery mod at sort of a master level, and it updates.
So okay, so now he's generating all this bytecode, right? And these are binaries. So he's got this in the PR, and he's going to change this though somehow. You could encode these in Go bin data, whatever you want. I don't think it's a big deal to merge this as is. I'm just saying. So
no, anyways, I need to change it.
Okay. So he's got these binaries, and then those binaries are, so then this backend sync says, okay, it receives the receives the updated state space, and then it uses the diff state thing that he showed you earlier to say, oh, I have a new service. It's 12.0.0.2 or whatever. I need to write a new service out. So then that thing decides to write a new service out, and it generates an Ebpf map, which
It
is like,
writes to an Ebpf map that's already there.
yeah, okay. So it's just writing something to an Ebpf map that already exists. It does a mutation on the map. Does it rewrite the whole map, or does it just do a point mutation?
Literally just adds.
It mutates a key.
entry.
Okay, so you can edit the map anywhere, like a key. It's kind of like IPVS that way, sort of. Okay.
Yeah.
So then he writes a key to the map to update whatever the thing is that he's updating, and the Ebpf rule. And then next time a packet comes in, if it's destined for one of these cluster IP VIPs, right? So if it's destined to this new thing here, before we even hit the kernel, that packet's IP address gets rerouted, right? So you have a packet diagram, right? So that
rewritten, even
rewritten. So literally, you go in here and you literally you change this value, right? Mm-hmm. So literally that gets rewritten. So you're still in here, and then that packet gets rewritten,
and then forwarded onto the kernel. And the kernel just sees pod to pod.
And then the kernel sees it. So if you run TCP dump, the kernel thinks you're going from, I guess the kernel thinks that the source IP is the node, right?
No, it thinks it's the pod where the client called the connect for. So if you were in a temporary client pod and you curled a service.
So what if I'm coming in from the outside world, if I was doing like a node port, or if I was doing an external?
Here's some harder things. You would hook into a different Bpf hook point, and that's like one of our next items on the agenda.
That's why you haven't done node port yet. Okay,
all
right.
Node port's a lot harder. Yeah, well, not a lot harder, but you can't really just trick the kernel anymore because you're coming in and out of a network. Whereas here, you're pretty much in the same network. You're just defining VIPs. Right, you're in the cluster overlay. You're in the pod network.
Scott is asking, does that mean we retain the source IP? Not any. Well,
no, we do. We do, Scott.
So how do you get to return? How do you get to? Where do you retain it?
Because we never touch it. All we do is rewrite the destination IP, and then the kernel sees a connection from pod A to pod B.
Sends it back. Okay, so you get to keep the source IP. Yeah. Okay.
So there's no NAT. I mean, it's like a fake NAT, pseudo NAT.
Yeah. Okay.
It's fun stuff. And I actually wrote I pulled, I guess that's in the wrong thing. I have a link. I have another repo that I made that exemplifies like the basics of how this works. That just like manually shows how the program works away from the KPNG control plane.
Okay.
And that's nice to check out too.
Okay, I'm going to put some links in here before you go for folks. So we have our entry alive hackmd. Nobody uses it. Chinchi never uses it. I'm the only one that uses this. Hold on, episode. Whenever a meme and Chinchi and everyone else does shows, they always just make their own notes. But I have this hackmd, the entry alive hackmd.
Wow, I think I've seen a link to that.
Okay, and it's like a book about all the things we do here. Can't tell you how many times this link has probably showed up in this hackmd. Okay, cool. All right, and then my favorite, eBPF is Turing complete. That's your homework. You have to tell me whether this is true or not.
Gosh, back in college.
He says he won this argument. Anyways, he got into some fight with his. Oh, to use traditional definition of Turing completeness, this means it cannot simulate the infinite tape of a Turing machine because you can only run 1 million instructions in eBPF. Okay, so that's why it's not Turing complete, because you can't run 1 million and one things.
That makes sense.
Okay, so all right, but anyways, Turing complete network rewriting logic stuff in upstream K8s. You saw it here first. Thank you, Andrew Stoycos.
Thank you. That was awesome. we'll do more. There's more to come. There's still a lot of work to do here. So reach out if you want to get involved. And, after we get the POC merged upstream, we can keep iterating, make it better.
Andrew Stoycos' tour de force of the KPNG Bpf implementation. Okay. And big thanks to our Cilium friends.
Yes,
because if this big thanks to Cilium friends. If the eBPF community and the Cilium folks hadn't done a lot of this stuff in the CNI and sort of thought about it and worked through the kinks and made libraries and containers and all the rest of it,
this would be a lot harder.
We wouldn't be here today. So, all right. Yeah. And of course to Mikhail for building all the KPNG stuff for us to put these backends into. So, all right. Thanks everybody. We'll see you all later. Thanks everybody for showing up. Andrea Live. Like and subscribe.